The understanding of phase diagrams for alloy systems is extremely important because there is a strong correlation between the microstructure and the mechanical properties. And the development of microstructure of an alloy is related to the characteristics of its phase diagram. In addition, phase diagrams provide valuable information about melting, casting, crystallization, and other phenomena. So after studying this chapter, we should answer the following questions. When we combine two elements, what is the resulting equilibrium state? In particular, if we specify, for example, in the copper-nickel system, when we know the composition, which means the percentage of copper versus the percentage of nickel, and the temperature, we should be able to identify how many phases may form in the system, and what is the composition of each phase, and what is the amount of each phase. To answer the previous mentioned questions, in this chapter we will examine solid solution by introducing the concept of an equilibrium phase diagram. A phase diagram depicts the stability of different phases for a set of elements. For example, the iron-carbon system or the nickel-copper system are the systems that we're going to study in this chapter. From the phase diagram, we can predict how the material will solidify under equilibrium conditions and what phases will be expected to be thermodynamically stable, and the composition of each phase and the amount of each phase. Since the major objectives of this chapter are to explore the formation of solid solutions by introducing the concept of phase diagrams, so let's review what is solid solution. We learned solid solution in chapter 4. A solid solution, if you can recall, is a solid materials in which atoms and ions of elements constituting it are dispersed uniformly. So a solid solution is formed when the solute atoms are added to the host materials, which is called the solvent. And the crystal structure of the solvent is maintained. There's no new structure or composition are formed. The solute may incorporate into the solvent crystal structure substitutionally or interstitially. So the key word here is dispersed uniformly. There's only one crystal structure. There's no new structure formed in the solid solution. Now, before talking about the term phase, let's see if the terms we already know are sufficient to describe a system. So we already learned substances and states of matter. For example, states of matter includes liquid, solid, gas, 3 states of matter, right? So consider the 3 simple mixtures we have here. The first one is sugar partially dissolved in water. So we have a syrup and then sugar on the bottom, and then we have the second one is sugar completely dissolved in water, and last one is mixture of oil and water, which are actually not mixtured. It's just they cannot mix into each other. We have oil and then water layer. So now, based on the 3 simple mixtures, think well the terms we already know, the substances and state of matter be sufficient to describe a mixture. As a review, we have learned matters in our chemistry class. So matters can be classified into different categories based on different characteristics. First of all, matters can be classified as pure substances or mixture, depends on the composition. If the matter has variable composition, it is a mixture. If it's not, if the matter has constant composition, it is pure substances. And for pure substances, we can further classify the material into element or compound. So if the substances is separable into simpler substances, it is compound. If it's not separable into simpler substances, it's element. For example, helium, just one element, that's an element, or just one type of atom, that's element. And compound, for example, water, pure water is a compound because it can be separable into the hydrogen and oxygen. And for mixtures, we have homogeneous and heterogeneous mixtures. Depends on if the mixture is uniformly distributed throughout. The two examples for homogeneous, for example, if we have a cup of tea with sugar melting in, it has uniform structure throughout, but for wet sand, it has a mixture of water and sand. It's not uniform throughout, so it's heterogeneous. And now, with the review of the matter or terminology associated with the matter, let's answer the following questions based on the three different mixtures we have. First, in the solution of sugar completely dissolved in water, what substances are present? Well, it has sugar plus water. Okay, two substances are present. Based on the definition of substance, a substance is matter which has a specific composition and specific properties. So, sugar and water, there are two substances. And in the solution of water completely dissolved in, or sugar completely dissolved in water, what states of matters are present? Well, it's just one state of matter, which is liquid. Number 3, in the solution of sugar partially dissolved in water, what substances are present? Well, same idea, right? The substances are still sugar plus water. And now, in the solution of sugar partially dissolved in water, what states of matters are present? Well, now we have two states of matters. We have liquid and solid. Number 5, for a mixture, can you predict the number of states of matter present by knowing the number of substances present? Well, the answer should be no. There's no specific number of states based on the number of substances present we can predict without any further information. Because based on the previous 4 questions with 2 substances present, sugar and water, right? The number of states can be just one state, which is the liquid state, or can be 2 states, liquid state plus solid state. It may also be one solid state only at low temperatures. So that's why we cannot predict the number of states of matter present by knowing the number of substances. The next question is the mixture in the mixture of water and oil, what substances and states of matter are present? So the substances will be water and oil. And the states of matter, there's only one state of matter, which is liquid, since both water and oil are liquid. So the next question is, what is the difference about the mixture of water and oil compared to pure water and or pure oil? Because all of them are just liquid. One state of matter, liquid, but clearly they're not the same. And what is the difference? Well, the difference, first of all, the mixture of water and oil looks different because there is a distinct boundary between the water and oil in that mixture. So we can say there are actually 2 portions of liquid. They don't mix together. So it's a liquid but has 2 portions. Or we can say this system or the liquid is heterogeneous. And for pure water and pure liquid, it's also liquid, or pure oil or pure water, it's also liquid, but there is only one portion of liquid, which is a uniform liquid, or it's homogeneous liquid. So now the final question is listing the substances and states of matter present sufficient to describe a mixture? Or based on all the questions we just answered, the answer to this question should be no. Because the mixture of oil and water, for example, has only one state of matter, which is liquid, yet it is clearly different from pure water and pure oil. So, because we cannot, with just saying liquid and water plus oil, we cannot actually visualize what the mixture look like. It doesn't give you that boundary thing, right? So we need a way to predict what the mixture actually look like. So then clearly we need some terms that can describe a mixture more accurately. So the terms we will use are component and phase. Component is a chemically independent constituent of a system, or it is the pure elements or compounds which are present in the alloy. For example, in the copper, zinc, brass, the components are copper and zinc. Phase is a homogeneous portion of a system that has uniform physical and chemical characteristics. So based on this definition, every pure material is considered to be a phase. Every solid, liquid, and gaseous solution is considered to be a phase. Now let's practice the new terms we just learned, component and phase. For sugar completely dissolved in water, it has components. How many components? 2 components, right? The 2 components are just water plus sugar, and there is 1 phase because completely dissolved, which is the liquid phase. And sugar partially dissolved in water has, again, the components are sugar and water. So this is the system of sugar plus water. So the components are always sugar plus water, 2 components, and number of phases are 2 because it's partially dissolved. So we have liquid plus solid phase. Next, a mixture of oil and water has oil and water are the 2 components, and the phases is just 1. No, not 1 phase. It should be 2 phases, 2 liquid phase. Okay, again, the definition of phase is chemically and physically distinct or distinctive. So it's chemically distinctive and also physically they are different as well. So 2 phases. Solid sugar has 1 component and 1 phase. The properties of materials depend on the components and phases that are present. The components are determined by what we mix together to make the materials. However, we need some way to predict what phases will be present in the system. So we do this by using a graph called the phase diagram. A phase diagram is a map showing what phases are present as a function of temperature and the amount of each component present. This is the sugar-water phase diagram. So this phase diagram is plotted as a function of temperature and the amount of sugar. And we will only focus on 2 component phase diagrams. In other words, we only have 2 components for each phase diagram we're going to study in this course. So in this phase diagram, the components we have are sugar and water. The amount of the 2 components added up to 100%. So although we have the weight percent of sugar, when we have 100 minus weight percent of sugar, we'll have the weight percent of water. So, for example, if we have 20% of sugar, then 80% will be water. If we have 60% of sugar, then we will have 40% of water. So, at each given temperature and the component amount, we can find from the phase diagram what phases are present. So the phases present on this phase diagram are liquid solution phase at lower sugar concentration. Well, think about if you just put 1 scoop of sugar into a whole glass of warm water, it will dissolve immediately or resolve immediately, right? There's no solid phase left, so it forms one phase. It's just liquid solution. In another scenario, if we put a lot of sugar, for example, 1 whole cup of sugar in 1 cup of water, you will have liquid solution plus sugar or solid sugar. So we will have 2 phases, liquid plus solid phase, at when the sugar concentration is higher. Okay, some questions or some information we can find from a given phase diagram. First of all, what components are present in this phase diagram? Well, the components, check the y-axis or the horizontal axis of the phase diagram. Those are the components. We have 2 components, sugar plus water. And second, what phases? Well, you can find from the regions the phase information on the phase diagram. What is the significance of this blue line labeled solubility limit? Well, for many alloy systems and at some specific temperature, there is a maximum concentration of solute atoms that may dissolve in the solvent to form a solution. And this maximum concentration is called the solubility limit. The addition of the solute in excess of this solubility limit results in the formation of another solid solution or compound that has a distinctly different composition. For example, in the sugar-water system, initially as sugar added to water, let's say at room temperature at 20 degrees Celsius, when sugar is added to water, initially a sugar-water solution or syrup is formed. As more sugar is introduced, the solution becomes more concentrated until the solubility limit is reached, or the solution becomes saturated with sugar. At this time, the solution is not capable of dissolving any more sugar, and further additions simply settle to the bottom of the container as the form of solid sugar. So thus the system now consists of 2 separate substances, a sugar, water, syrup, liquid solution, and solid crystal of undissolved sugar. The solubility limit depends on temperature. So this plot is actually the dependence of the solubility or the maximum concentration of sugar as a function of temperature. For example, at room temperature, this is the maximum amount of sugar can be dissolved in water. When we increase the temperature, right, based on our experience, we know we can dissolve more sugar in water. For example, this is the solubility or maximum concentration of sugar can be dissolved in water, and as we increase the temperature more and more, we measure different value of maximum concentrations of sugar at different temperature, and then we connect those concentration points, and this solubility limit line will be formed on the phase diagram. So now let's do one example. The question is, what is the solubility limit for sugar in water at 20 degrees Celsius? So we can draw a horizontal line at temperature 20 degrees Celsius and find the intersection of the temperature line with the solubility limit line, and we read off the corresponding percentage of sugar, the amount of composition from the horizontal axis, which is 65%, which means at 20 degrees Celsius, the solubility limit of sugar in water is 25%, which means we can only dissolve a maximum of 25% of sugar in water at room temperature. So, to answer this question, we know it's 65% of sugar, which means at 20 degrees Celsius, if the concentration of sugar is below the solubility limit, we have liquid solution. All the sugar will be dissolved in water to form a single liquid solution or syrup. But if we excess this solubility limit at the given temperature, we'll have two phases, which will be the syrup plus the undissolved sugar, which is the solid phase. There are three externally controllable parameters that can affect the phase structure or the phases present in a given system. The three parameters are temperature T, pressure P, and composition C. But in most cases, the pressure will be kept as a constant value, which is at 1 atmosphere. So in this course, we will just focus on the parameters temperature and composition. So we still use this water-sugar system as one example to describe the effect of the temperature and composition. So change the temperature can change the number of phases. For example, from path A to path B, well, we keep the composition as a constant value. Is about 70% of sugar. When we put 70% of sugar in water at 20 degrees Celsius, we will have two different phases because it's landed, our point A is landed in the two-phase region, liquid plus solid. When we increase the temperature while keeping the composition at 70%, we will enter the one-phase region. So the number of phases decreasing from two-phase to one phase, from liquid plus solid phase to single liquid phase at 100 degrees Celsius. So this is easy to understand. At room temperature, we cannot dissolve 70% of sugar in water because we know the solubility limit is about 65%. So we cannot dissolve 70% of sugar in water, but when we warm the water up, the undissolved sugar will be dissolved into the water or into the syrup. So we will end up with one phase only because increase the temperature, increase the solubility of the solute. And second, for the composition, when we change the composition, we will also change the number of phases present. So the second pass from pass B to pass D, we keep the temperature at 100 degrees Celsius, but we increase the composition. We increase the sugar from 70% to 90%. Now the number of phases will change from one phase region to two phases region, because when we add more sugar into the water, it cannot dissolve anymore. So the undissolved sugar will be left as the solid sugar phase. So change or altering the composition can change the number of phases present in the system.